So in this video we're going to go over reduced row echelon form of a matrix, or REF is what we'll frequently shorten that to. So a matrix is in reduced row echelon form if it meets these four criteria. And what we're going to wind up doing ultimately is solving systems of linear equations by using what are called elementary row operations, and using those operations to manipulate the matrix into reduced row echelon form. And from this form, we'll be able to deduce the solution set for the system. So as long as you meet these four criteria, you are in reduced row echelon form. So if you just kind of walk through them, it says any row that contains only zeros has been moved to the bottom of the matrix. So this is criteria number one. So this first matrix, there is no row that contains only zeros, but in the second matrix, the third row contains all zeros, and it's at the bottom of the matrix, so it meets that criteria. And here I actually have two rows that are all zeros. Both of those rows have been moved to the bottom of the matrix. So if you get an all zero row occurring in any row that isn't the bottom, you move it down. The first non-zero entry in any row has to be a 1, the first non-zero entry. So when you look at the first matrix, here's the first non-zero entry in this row, and it's a 1, so it meets criteria 2. Here the first non-zero entry in row 2 is a 1, so it meets that criteria, and the first non-zero entry in row 3 occurs here, and it meets that criteria. Over here we have a non-zero entry that isn't a 1, but we still meet this criteria because the first non-zero entry in that row is a 1. So it's okay for a row to have non-zero entries that are not 1, but the first non-zero entry has to be a 1 in any given row. So each of these three matrices meet criteria 2. The leading one of any row in the matrix is positioned in a column that is to the right of the previous row's leading one. So if I walk through and think about that criteria, that says, hey, the first leading one has to be to the right of any previous row's leading one. So you have to ask yourself, is that true? So here, the first leading one is right here in column 1. And it's going to be vacuously true that it's to the right of all preceding rows leading ones, because there are no preceding rows. Here, this row's leading one is positioned to the right of the previous row's leading one, and this leading one in row 3 is positioned to the right of each of the other two rows' leading ones. So if you look through each of these examples, the leading one is always going to be to the right of all of the previous rows leading ones. Here, row 3 has no leading one, so it meets that criteria kind of in a vacuous way. So here's my leading one. My first non-zero entry is a 1. The next row down, its first leading one is positioned to the right of this row's leading one. So we meet that criteria. And then the last one is all other elements in a column that contains a leading one must be set to 0. So here I have a leading 1. Everything else in that column needs to be 0. So the two entries below it are 0. Here I have the leading 1 for row 2. So every other entry in the column that contains this leading 1 must be a 0. Here I have a leading 1. The other entries in that column are zeros. Here I have another leading 1. The other entries are zeros. And the same over here. Here's my first leading 1. Everything below it has been zeroed out. The second row has its leading 1 here, and everything above and below it has been zeroed out. The last column here we don't need to worry about because there are no leading ones in that column, so it's okay for there to be 0 entries, non-zero entries, numbers that aren't a 1 or a 0, everything's good to go. So as long as a matrix meets these four criteria, we are in reduced row echelon form, And what we're going to discover is this is a form that will allow us to deduce solutions. And the reason is if we're working, for example, with an augmented matrix, these columns are going to represent our variables, and we'll have the constant terms here, and we're going to discover as we move forward we'll be able to interpret solution sets from this form.